Big O notation is a way of measuring the efficiency of an algorithm or an operation. Before we start, I want to briefly cover logarithms. So I'm here in GeoGebra, which allows me to plot a mathematical graph. Again, this is different from graph theory graphs that we've looked at in one of the previous videos. So here we've got y equals log base 2 of x. And I'm not going to fully explain what that means. Maybe I'll add a link in the description to something that explains logarithms in more detail. But let's see what that means in terms of algorithmic complexity. So let's also add y equals x to the graph, and we can see what this means. So with y equals x, our input is going to be x, and our output is going to be y. And as x increases by 1, so if we take this point here at coordinate 4, 4, as the x value increases by 1, so x becomes 5 instead of 4, the y value also increases by 1, so we get 5, 5. Now, before we have a look at logarithms, let's add something else that might be a little familiar. Let's add y equals 2 to the power of x. So y equals 2 to the power of x is exponential growth. And you can also see here that we've got kind of like a mirror image across the y equals x. The y equals 2 to the power of x is kind of the mirror image of y equals log base 2 of x. If we add some points to this graph, like we've got here in this tab, we've got A, B, C, and there's D just above here. So A is going to be the coordinate 1, 2. So x value 1, y value 2. And even though all of these points are on this graph, we can notice an interesting property of exponential graphs. As the x value, as the input, increases by 1, so here we've got x equals 1, x equals 2, x equals 3, and x equals 4 up here. You can also see this on the side. As the input increases by 1, the output, the y value, doubles. So we start off with 2, and then we have 4, and then we go all the way up to 8, and then all the way up to 16. So with y equals x, this red line here, which is linear, our input is always the same as our output, or as our input increases, or as our input doubles, our output will also double. With an exponential curve, as the input increases by 1, the output basically doubles. In this case, it does double, but if we change the graph ever so slightly, it can still be exponential, but it won't be perfectly double. And as well, if we have the same points, or very similar points, but this time on the logarithmic curve, we can see the inverse property. So as the output this time increases by 1, so y value of 1, 2, 3, and 4, in order to achieve that output, we have had to double the input from 2 to 4 to 8 to 16. So how does this relate to the efficiency of an algorithm? Well, if I bring up the visualizer again, and let's have another look at binary search. So in the video about linear search and binary search, we discussed how binary search is much more efficient than linear search, but let's look at exactly why. I think I did mention this kind of example in that video as well, but we're going to take a deeper dive. So in a linear search, where our target is maybe E, and we've got A, B, C, D, E, F. A linear search would say, okay, is the first item what we're looking for? No, let's move on. Is this item what we're looking for? No, let's move on. No, move on. And here we go. So how many of these checks did we have to do? We did 1, 2, 3, 4, and 5. This collection has a length of 6, so the maximum possible would be in the case where we are looking for f, when we are looking for the last value in the collection. In this case, we have to check every single value. Well, what if the collection was to double in size? Instead of having 6 values, it was to have 12 values. Well, in this case, the maximum amount of checks that we would have to do would double as well. We would still have to check every single item up to the last one. So we can kind of see a parallel here between linear search and y equals x, this linear line. In binary search, however, we don't check every single value. In fact, we check roughly we get rid of half of them at once. If we wanted to do a binary search, we check the middle item but left, and then we say, nope, our target should be to the right of that. So we take this collection of 3, this sublist, this sub-array, and we check the middle one. Nope, it should be to the right. And now we've done only 3 checks. But with a binary search, if we were to double the size of the collection to 12, we would only have to do 1 more check. We would have to do 4 in total. Or potentially less. But this idea now of doubling one thing and increasing something else by 1 should sound quite familiar. And that's because the binary search runs in logarithmic time. If our array has a lot of items, maybe 16, it should take log of 16 checks to find the item that we're looking for, or maybe less. Big O notation doesn't try to represent the time complexity or any kind of complexity of an algorithm perfectly. And this is a bit of a strange concept, especially for beginners. I know that I struggled with this for quite a long time. But if we just have another look at this graph, or of this logarithmic curve, we can see something that's a bit odd. So binary search runs in logarithmic time complexity. So surely what this is saying is if we have a collection of 1 element, then we should have to do 0 checks in order to find the target. And that doesn't really make sense. It certainly doesn't make sense that if we have an empty collection, that we would have to do negative checks. Now, we can't have a collection of a negative size. So anything to the left of this doesn't really matter anyway because we can't represent it. But we can have an empty collection, and we can also have a collection with 1 element in it. So when we say that something is big O of log n, or it is logarithmically complex, that doesn't mean that the time taken for the algorithm to be completed is exactly log of the size of the input. It just means that it has this familiar property that if we were to double the input size, the output would take a fixed amount of time more. It wouldn't, the time taken wouldn't also double like a linear algorithm. If we have an array, and in this case we have 6 items, and we want to access one of the items, maybe index 3. Well, we can always, we know where that's going to be. If we have the starting point of the array, which we usually do if we're storing an array in programming, we can say, okay, we go to the start of the array and we go along by 3 points. And because everything in an array is stored next to each other in memory, we don't have to do any checks. We don't have to check the 0th item or the first item or the second item. We can just jump all the way to where we need to go. If the array was double the size, if it was 12 elements instead of 6, we would still be able to do the exact same thing, even if we want to access an element that can't currently be represented. If we wanted the 10th item, we wanted to go to index 9, we could do the exact same process and it wouldn't take any longer. So what this means is that accessing an item in an array has constant time. And if we were to represent that on GeoGebra, that would look something like, let's add a new input. Maybe let's go to here, and y equals 1. So it would be a straight line. As the size of the input increases, the output stays the same. It doesn't matter. So that's what it means to have constant time, and accessing an array has constant time. It doesn't matter how big the array is. If we know the starting point and the exact location that we want to go, we can jump ahead to wherever we want to go. And we can represent that with an O and in brackets a 1. With a linked list, however, we don't know where each element is physically stored. With an array, we can utilize the property that everything is going to be right next to each other and in the correct order. But with a linked list, all we have is our starting point and a reference to where the next value can be found. So if we wanted to find the 3rd element, if we wanted to go to the equivalent of index 2, we would need to go to the next item, and then only from there can we go to the next item and find index 2. Now, if we wanted to get to index 2 specifically, then our collection could be double the size. It could be of size 8 or of size 16 or of size 1000, and it wouldn't matter. We could still get to index 2 by going from the starting point, next, and we're there. So that would be constant time. But if we wanted to access a random item or the average of all items, that would be increasing. Because if we wanted to get index 4, the most amount of moving to the next, the most amount of operations we would have to do is 4. But as soon as we add a 5th, or if we add a 6th element, we would have to go across by 5. So let's just come back a bit. We've got 4 elements. The most amount of operations we would need to do in order to reach a random element in our linked list is 3. We have the starting point, next, and we're there. If we add in a 5th element, the most amount of operations we have to do increases. And that happens every single time we add a new element. And so while accessing a specific location in a linked list could be considered constant time, to access a random item in a linked list is O of n, or linear time, x equals y, or sorry, y equals x. And you may be thinking that, well, no, surely the average amount of checks that we have to do is going to be half of the maximum amount of choices that we have to do. In this case, that would be half n, where n is the length of the collection. But big O doesn't care about being completely precise. All we care about is the order of magnitude. If we have half n, that is still dependent on n. So as the collection doubles in size, so will the amount of checks that we have to do. Even if we have to do, even if we only have to do half n checks every time, because we've got that dependency of linear time, it's considered big O of n. In fact, the big O comes from the German word order, as in order of magnitude. So let's have another look at bubble sort. If you remember, the bubble sort algorithm, after the first iteration, after we've looked through every single item, will guarantee that we have the largest item, assuming we are sorting in ascending order, the largest item will be guaranteed to go into the correct position after the first iteration. After the second iteration through the whole collection, we will guarantee that the largest and the second largest will be in the correct position, and so on. One iteration through a collection is going to be O of n, just like linear search. So if the collection that we need to sort is double the size, one iteration is going to do double the amount of checks. This is linear complexity. If one iteration guarantees that one item will be in the correct location, and 2 iterations will guarantee that 2, and 3 iterations will guarantee that 3 values will be in the correct location, we need to do at most n iterations in order to confirm that we have sorted the algorithm. So as the collection doubles in size, we would have to do 1 iteration, 2 iterations, 3 iterations, all the way up to n iterations at most. So the amount of iterations we have to do is n, and the time taken for each iteration is also n. So our time complexity is going to be O of n multiplied by n, or O of n squared. Big O notation is a very tricky concept, but once you start seeing it more and more often, and you start to recognize big O notations from algorithms that you see, and then eventually get onto complexity analysis, which is where you write your own algorithms and you say what the big O notation, the complexity of your own algorithm is. That's really quite challenging, but once you start doing it more and more often, it will get easier and easier. We've been talking about time complexity throughout this video, but big O notation can also be used to measure the space complexity in a very similar way. So instead of caring about how much time taken, how much time does the algorithm take to execute, space complexity deals with how much storage do we need to represent or to keep track of everything that the algorithm needs to keep track of. This isn't quite as common as time complexity, but it's also quite important. But it does have very similar ideas behind it. If you can get used to time complexity, space complexity won't be too difficult after that. Thank you for watching, and I hope this was helpful.